Welcome back. We were discussing nonlinear models for classification and we talked about decision trees. So the next thing that we want to talk about are neural networks. Okay. Even though the lecture is on neural networks, we would begin with a single neuron model, okay, which is popularly known as a perceptron model, okay, right, and then gradually evolve from there. All right. So the idea is this. Most living animals, including humans, of course, are capable to perform certain, actions, which is one that, have seen something and then able to recognize it the next time. Okay. All right. Based on how strong the memory of that particular animal is, it's like it gives the power of recollection by that amount of magnitude. Okay. So basically what happens is the artificial neural networks mimic this. Okay. So they mimic the hundreds and thousands of neurons that are there in the brain of animals and humans, right? Okay. And but they can only mimic this partially, not in a fully functional sense. And mostly the mimicking job is for recognizing patterns or bits in the signal, right? So which is a basic function. Artificial neural networks do not have the ability to recall an answer to a search problem at a later time. Okay. So it's something like a visual cortex, something like what a visual cortex performs for a human being, right? Which is primarily for an object recognition. So, when we talk about foundations, we talk about perceptrons. And the neural nets. So the foundations of neural networks are perceptrons. And the other one is the gradient learning, right? Which we have discussed in some detail when we talked about regression models, if you recall, right? And then there are non-threshold, and these are functions. So non-threshold activation functions. Some of the popular ones are sigmoid, rectified linear units, right? tanh, and there is a new one, SBAF, which is called Saha-Bora activation function. Okay. All right. So the building blocks are, one of the primary building block is a perceptron. So it's a simple single neuron model. Capable of, performing simple enough tasks. Okay. All right. And the way it works is this, that, I have one neuron over here, which is a threshold activation unit. Okay. So it's a threshold activation unit. So it basically what it does is, a neuron, particular neuron, which is this one, will be fired once you reach this threshold. Okay. So once you reach this threshold, the activation, the neuron will be fired, and there is also a bias term that comes in, which is basically a barrier which you need to overcome if the threshold value has to reach the output layer, if the threshold value has to reach 0 for activation. So till 0 you can have some values from negative to 0, right? And from a classification problem, what this implies is, you have a function, some sort of a function, right? Okay. And you apply you feed the inputs to a function. So what the function does is that the function acts on the input and produces a number, one number, right? Now, if that number exceeds your bias, your neuron is fired, okay, all right, and then you will, and this number typically is a positive number, let's say, I mean, depending on how much positive you want. Basically, it has to cross the bias barrier, so that for all the positive values that it generates, these values will correspond to one class level, and below that threshold activation, whatever values you will generate by using the same activation function, you are going to generate and correspond those values to the other level. Okay, so this, I mean, a binary classification, this is the way a binary classification works. I mean, as far as a single neuron perceptron model is concerned. So what we have is a bunch of inputs here. With a bias, there is a threshold function that will work on this weighted combination, and then you will give some weights here. Let's say W1, W2, W3, so on and so forth. Okay, so give some weights here. So what will happen is this weighted input plus bias, you will have some threshold that will act on it, right? Some threshold activation that will act on it, produce a number. If that number, is greater than some threshold value, your neuron will be fired and you will, generate class levels. And this is the way it works. Okay. So, I mean, typically what it means is, let's talk about an image recognition problem, right? I mean, your target level, when there are images bright images, there are dark images. Let's say that the bright images are labeled +1 and the dark images are labeled -1, right? Your target is to recognize bright images, okay, which are +1. Okay, so the way it works is, you have a bias unit, okay, all right, and this is your neuron, okay. And there are a bunch of inputs, and these inputs corresponding to the pixel values. Okay, all right. So it's a minus, let's say -1, +1, +1, -1, and then you have some weights: 0.7, -0.2, 0.1, 0.9. Okay, and you have a fixed bias unit, and the goal is to classify the image. Goal is to classify the image as bright or dark. Okay. Okay. So what are the steps in it? I mean, if I have to just, write it down in steps. So let's just, quickly go through the steps. So the first step is that your S is nothing but the weighted combination of the inputs. So you write it this way. Okay, all right. And then the next step is, you provide this guy, okay, to the activation unit. Basically, it's like the way how a function works, right? So this S is that with W transpose X, you apply some activation on this and you produce some output, right? Okay, all right. Now, remember, I mean, in a supervised problem, you already know the target levels, right? Okay, and these are the output levels that you are generating, correct? Okay, so therefore, I mean, there will definitely be some error, correct? Which is compute the error, which is what? The difference between the target and the output. Okay. Well, let's say you hit the jackpot and your error is 0. You do not have to do anything, come out of the loop, terminate the program and say the classification objective is reached. But let's say it's not. I mean, initially what happens is, you start with some arbitrary combination of weights and inputs, right? Your inputs are fixed, but your weights are arbitrary. And typically you begin with by, having a horrible error to begin with. I mean, a horrible error, right? And then you gradually reduce the error. So when you reduce the error, that's where this gradient learning comes into play. Okay. So what you do is, in the next step, you calculate the weight, okay? Because what will happen is, you started with some random weights, right? You don't really know what these weights are. So, and you find out that these random weights did not work well. I mean, the error between the target and the output is really high, right? So you have to recompute the weight and update the weight accordingly. So how do you do that? You have the error, right? And then you have the sample points, right? And then you multiply that by some constant, some positive constant, alpha. Now this alpha, once again, it's sort of known as a learning rate in your neural network. But what happens is this alpha could be set to 0.1, 0.01, so on and so forth. The idea is you really do not want to set the alpha too high, okay, or too low. Okay, so there needs to be some balance in the sense that the gradient in multiple dimensions need to be adjusted accordingly. Okay, so let's say I have this. Okay, so typically this is what I mean. So this is my new delta W, and once I have that, I actually update the weight by using the previously used weight plus. Okay, all right, which is nothing but delta W. This is nothing but delta W. So this is the weight update rule, and so together these 5 steps, when you do that, you update the weight and recompute S, provide to the activation unit, recompute the error, and this is an iterative process. So these 5 steps combined is the basic perceptron learning rule. Okay, all right. So we will see an example now. So what I have here is, so it's an example, some inputs, okay, with a -1 bias, right? And these are the weights arbitrarily chosen. In fact, okay, and so this is nothing but my W transpose X, but W is the weight vector and X is the input vector. Okay, all right. So I mean, I sort of recreate the perceptron learning step by first computing what is W transpose X. So S is W transpose X and is nothing but, you know, the column vector multiplication. So 1 times minus 0.5 minus 1 times 0.7. So let's do that. So 1 times minus 0.5 minus 1 times 0.7 plus 1 times minus 0.2 plus 1 times 0.1 minus 1 times 0.9. Okay, this turns out to be what, minus 1.2 minus 2.1, you know, turns out to be minus 2.2. This is a negative number. Okay, all right. So what is happening is, I mean, the next step is where you compute the output. So, you know, the output is f of s. Okay, now remember my target label is to recognize bright images, which is the labeled as +1, right? And with the negative values of the negative s, f of negative s, I'm not able to, you know, cross the bias barrier, right? So what I'm going to, my natural decision is, for such negative inputs not being able to cross the bias barrier, the output will be christened as -1. Note that the target label is +1. So therefore, I mean, you have error, right? Your error at the first step, I is equal to 1, is nothing but t minus o, which is 2. Okay, all right. So what do I have to do? Clearly, the first iteration didn't work, right? And so I have to recompute the weight. So how do I recompute the weight? I recompute the weight by, okay, and let's say heuristically set alpha equal to 0.2, and we'll come back to this later on in greater detail. I mean, this learning rate. Okay, all right, because I strongly believe unless you you know, figure out proper way of setting learning rates, or you if your learning rates are not able to adapt, it's like, like a cottage industry, like you are trying to make a doll using clay, right? Some clumps clay work and it doesn't work, so you dismantle it completely, break it down, do it again until you get the desired shape and everything that you want. Well, I mean, computationally speaking, you will end up doing a lot of iterations, and even though with the modern computing power, space constraints are not that much, right? And people really don't bother about time because most of the training happens offline. Ultimately, the idea is to get a pretty good accuracy, and it does. It will eventually get to a very good accuracy. But the amount of computational expense that you are investing is enormous, and I don't think, I mean, at least from the point of view of, trade-off between precision and computational expenses, I would always try to have a sort of a middle ground anyway. So which is why the learning rates come in handy later on. Okay, so not now. Anyway, so let's just compute all these. You have 5 units, right? So we compute everything. Delta W naught, which is what? Delta W naught, alpha is fixed 0.1, error is also fixed, which is 2, and the x side, so this is x1, right? So this is x2, so on and so forth, right? So you do that, and this is 0.2. Delta W1 is 0.1 times 2 times minus 1 equal to minus 0.2. Delta W2, the learning rate is fixed, error is fixed, the next data point is 1, so this is 0.2. Delta W3, same thing, right? 1 equal to 0.2, and delta W4 is this. Okay, so once we updated, once we computed, then the change in the weight, we will have to update, right? So what will happen is, what is the update rule? The update rule is Wi equal to the previous weight plus delta Wi. So what this will imply, your previous weights are this, these are your weights. Okay, all right. So this is W naught, this is W1, W2, so on, right? So you would add these guys with these guys to update the weights. So I'll just do one thing. So your new W naught is going to be W naught plus 0.2, right? Which is negative 0.3. W1 is your old W1 minus 0.2. Old W1 is 0.7 minus 0.2 is 0.5. W2 is your old W2 plus 0.2, which is minus 0.2 plus 0.2, it becomes 0, right? Okay, and then W3 is your old W3 plus delta W3, so which is your old W3 is 0.1, so in 0.1 plus your delta W3 is 0.2, so it becomes 0.3. Similarly, W4, your old W4 is 0.9, the update in the weight is minus 0.2, so you'll have 0.7. Okay, all right. So once I have that, so this is the second iteration, right? So what I'll have is that I have these guys. Okay, so I'll update the weights, right? And the weights are negative 0.3, 0.5, 0, 0.3 and 0.7, right? The inputs remain the same. Okay, all right. So the inputs are plus 1, minus 1, plus 1, plus 1, minus 1. Okay, and you expect the, if this is positive, and based on that, there will be a classification of +1 or -1. Okay. All right. So if the outcome is negative, then it's classified as -1. If its outcome is positive, then it's classified as +1. Okay. So let's retrace the steps. So what we do here is, again, we compute the S. S is nothing but W transpose X. So you know the W's, okay, you know the X's, right? I'm not going to, so what you will do is 1 times 0.3 minus 1 times 0.5, 1 times 0, 1 times 0.3 minus 1 times 0.7, okay. So what I'm going to do is, I'll just skip this and you can verify S is negative, okay. If S is negative, it's classified as -1. The actual target level is 1. So therefore, you still end up with an error, which is not good. So what do? Update the weights again. Okay, by the same update rule. All right. And if you do that, pretty much I'll just write down the updated weight straight away. I mean, instead of going through the same monotonous calculations, and I'll find that the new updates are this. Okay. All right. So what I'm going to do now is just replace the old weights from iteration 2 with the new weights that are just computed. Okay. So what are the new weights? Minus 0.1, 0.7, 0.2, 0.5 and 0.9. Okay, great. And then do this again. Okay. All right. So what I'm going to do, I have to recompute this. Okay. All right. So let's recompute. So I know that the inputs haven't changed. So now I have 1 times minus 0.1. So this is negative 0.1 minus 1 times 0.7, which is negative 0.7, plus 1 times 0.2, which is 0.2, plus 1 times 0.5, which is 0.5, minus 1 times 0.9. Okay. All right. So if I do that, I think updated weight vectors are not correct. I'm sorry about that. The updated weight vectors are actually in the next step. What will happen is 0.7, 0.2. Yeah, that's right. Okay. And then we iterate this again. So basically what will happen is the same thing will happen actually. I mean, I'll have a negative number, so I do it, so I update again. I'll update the weight again. And this time, by following the same process, what I'll obtain is, so this was correct actually. So this is 0.1, 0.1, 0.4, 0.7 and 0.3. Okay, so this is the fourth step. Okay, now, so what will happen is, at every step I'm going to recompute. So when I recompute with this, so I have 1 times 0.1. Okay, so I'll use this, minus 1 times 0.1, right, plus 1 times 0.4, plus 1 times, so basically what I should have done is, I apologize, I update the weights, right. So when I update the weights, I replace the old ones. So this is 0.1, 0.1, 0.4, 0.7 and 0.3. Okay. All right. So this is 1 times 0.1, minus 1 times 0.1, 1 times 0.4, 1 times 0.7 and minus 1 times 0.3. So what do you see? It's 1.1 plus 1.2 minus 0.8. So this is finally what I have is 0.8. Okay, good. So this is greater than 0, right? Okay. Now, if it is greater than 0, if I go back to the flow diagram, if it's greater than 0, I am able to classify this as plus 1. Okay. All right. What's my target level now? My target level is plus 1. Output level is 1. So, my error becomes 0. Okay. And therefore, after 4 iterations, the perceptron model has finally been able to learn the correct weight and was able to predict the true target level of the image. Okay, so I think this is a good point to stop.